What is the displacement binding experiment and why do we do it? Let's start with the why. Radioactive ligands are expensive. If you are trying to find a good antagonist for something and you have 10 candidates, in order to use saturation binding experiments to determine which one binds better, you would have to have a radioactive version of all 10 ligands, which gets very, very expensive. And depending on where you work, they may not even let you have that much radioactive material. With a displacement binding experiment, we only have to have one radioligand. So what we're going to do in this situation, imagine we want to test our 10 different potential antagonists. What we're going to do is we're going to get a radio-labeled version of the agonist and then do experiments using that and our 10 non-radio-labeled, or what we call cold, antagonists. That allows us to have inexpensive antagonists and just one expensive agonist. By doing this, we can determine also whether our antagonist is competitive, non-competitive, or allosteric. And so the simplest one is competitive, right? A competitive antagonist is an antagonist that binds to the same location as our agonist, and we can overcome the antagonist by simply increasing the amount of agonist. We can also outcompete our agonist by simply adding more antagonist. And so what we're looking at in our figure here are experimental results that would show us that the antagonist we are using is a competitive antagonist. For a displacement experiment, for a general displacement experiment, the way we do this is we add a bunch of radio-labeled agonists, we give it a while, we let it bind. That defines where our binding is going to start. We are then going to add our antagonist and watch as the amount of increasing antagonist leads to more and more radio-labeled agonists getting kicked off the receptor. And so let's look at one curve here to begin with. X-axis is just increasing amounts of antagonist. Again, as always, ignore the stupid units here. The y-axis is how much of our agonist is bound. So in this situation, on the lowest curve here, we added a low amount of agonist. This is the 0.03 here. This is the lowest amount of agonist that we're going to use. And so we started with this much binding. And then as we add increasing amount of antagonist, we start to see the agonist come off. When it comes off, the radioactivity or whatever we're using disappears. And so we can see that at this concentration of our antagonist, roughly all of our agonist is now gone. Each of these curves shown on the graph represents starting with more and more and more agonist. So as we add more agonist, the starting binding goes up, but also the amount of antagonist required to displace 50% of the agonist increases. As we add more agonist, it requires more antagonist to kick half of it off. And so, by doing this experiment, if we see that the IC50 of our antagonist increases as we increase the amount of agonist, that means it is a competitive antagonist. I don't remember if we have covered the concept IC50 or not, so I'm just going to very quickly do it again. IC50 is the inhibitory concentration 50. That is the amount of antagonist required to displace 50% of the agonist. So with a competitive antagonist, the IC50 will increase. It will move to the right as we add more and more agonist. With a non-competitive antagonist, we are not going to see that change in IC50. Non-competitive means that we cannot overcome antagonists by adding more agonist. And so the amount of agonist present is irrelevant. If the antagonist wants to bind 50% of the receptors, it is going to bind 50% of the receptors no matter how much agonist is there. And so with our displacement experiment, rather than seeing the curve shift to the right as we add more agonist, all we do is we shift where we start up. And the IC50 is identical for all agonist concentrations. And so if you see this, you know that your antagonist is a non-competitive antagonist. A third type of antagonist is an allosteric antagonist. And we have an entire lecture on allosteric ligands later on. But remember, an allosteric ligand binds to a location other than where the agonists bind. So they're binding to different locations. And so it is possible for one to bind and then the other to bind. It's not a one or the other situation. So if our antagonist is an allosteric antagonist, when we increase the amount of agonist, our IC50 is going to go up. But notice that at the highest concentration of agonist, it doesn't matter how much antagonist we add, no matter how much antagonist we add, we can never displace all of the agonist. So in terms of the IC50 shift, it looks like our competitive displacement. It goes to the right. But notice with competitive displacement, we can always get down to zero binding if we add enough antagonist. Here we can't, because when the antagonist binds, it does not block the agonist from binding. It simply makes it less likely that the agonist is going to bind. And so, even if it is a very low likelihood, if you add enough agonist, you're going to get some binding. And so we can never get this down to zero binding. Something we'll see about allosteric ligands, though, is they don't have to act as an antagonist. In this graph, what we're looking at on the x-axis, we have the binding of, we're adding amounts of an antagonist, an allosteric molecule called alkyronium. and we did displacement bindings with it with two different radioactive agonists. One of them is atropine, one of them is this methyl QNB. With the QNB, we see a curve like we would expect. As we add the allosteric ligand, the binding of our agonist goes down, just like we saw on the last slide. But the same molecule of L-geronium actually increases the amount of atropine binding. So allosterism gets really, really crazy and hard to predict. We'll see more about that in another video. Another thing that makes things complicated is efficacy. And in this case, we're going to define efficacy as the change in conformation of a receptor from inactive to active. Remember that can happen in the absence of ligand. And so imagine a situation where we have a receptor that can be activated by the binding of a ligand or by the binding of a G protein. Or maybe it can become spontaneously active. If the conformation of our receptor changes before the ligand binds, most likely that is going to change the affinity of the ligand for our receptor, which means that the ligand is going to bind to our receptor differently whether the receptor is inactive or active. In our graph here, we are adding an agonist in this situation, oxotremolin. And we're just simply measuring its saturation binding to a receptor. This is not a displacement experiment. If we do it in the absence of G protein, all of our receptor is in the inactive state. And we get the curve here with the white dots. If we do it in the presence of G protein, we get the curve with the black dots. The curve with the black dots is shifted left. It is shifted to a lower concentration. And in this situation, it is 600-fold lower concentrations. So simply by doing our experiment in the presence or absence of G protein, we can get an answer that is 600-fold different. Our KD or EC50 is going to be 600 times different, depending on whether the G protein is there or not. Which simply means you have to keep that in consideration when you design your experiment. In which situation is relevant. And you need to report that so that if somebody else comes along and tries to do the same experiment, they know whether they need to add the G protein or not. Something else to keep in mind is that things do not happen instantaneously, especially if we add two compounds at once. We have a graph here with two different curves on it. The x-axis, we are looking at simply time after we add our compounds to our receptor, and the y-axis is just occupancy. If we add a radioligand or an agonist all by itself, we get the curve shape that we've seen before where it comes up steeply and then flattens out. If we're going to measure binding here, we need to wait long enough so that we have reached the plateau. If we measure the binding, in this situation, after 20 minutes, we are only at roughly 0.6% or 0.60% binding, when that concentration of ligand that we added is capable of 100% binding. We just didn't wait long enough. And so if we report 60%, that is going to be wrong. If we add a radioligand along with an antagonist, you can see that this curve is very, very, very shallow. The graph goes up to 200 minutes. It's over 3 hours, and we're still nowhere near plateauing. And so you need to be patient. With the radioligand competitor, you don't have all day. You can't wait 24 hours to measure your binding, because if you do, your receptor is going to degrade, something is going to happen. And so what you need to do is you need to report how long you did wait. You need to wait as long as you can, and then you need to report how long you waited so that somebody else can duplicate your experiment. I'll let you look at this. This is another slide looking at the effect of time on it, on what we see. Particularly, I want you to look at the one on the right. In this situation, we are adding an antagonist either 30 minutes or 4 hours after we added our agonist. And depending on how long we wait our agonist bind, we get very, very different concentrations for our IC50 of our antagonist. Our last slide here is a list of criteria for effective binding experiments. I would know these by heart. I would expect to be tested on them. So there are a number of things here. Number one, the binding of our agonist has to be saturable. We can't have something that just binds, its amount of binding goes up infinitely. Its binding has to be reversible and to be displaced by another ligand, assuming that we are going to measure it using a displacement binding assay. We have to have a second ligand that we can use to determine non-specific binding. We have to have enough receptor there to get enough binding to be able to measure it. If we can't get enough binding, we're going to have a very low signal and we're going to have error in our measurements. However, we can't have so much receptor that we soak up too much of the ligand that we added. We always assume that the amount of ligand that we added is the concentration floating around in the medium above our cells. But if half of our ligand sticks to a receptor, the concentration floating up here is now different. And that complicates things way beyond anything you want to deal with. So you need to make sure that the amount that sticks is negligible compared to the amount that you have floating around up here. You generally want to have high specific binding, low non-specific binding. You need to have agonist tracer ligands, and you need to have antagonist tracer ligands if you're going to do different experiments. We generally don't want to wait around forever, and so we want something that binds quickly with fast kinetics. And when we use a second molecule to determine nonspecific binding, that has to be different than the molecule we use for specific binding. You can't simply have a radioligand for specific binding and then use a non-radio labeled version of the same thing for nonspecific binding. It's not going to work. And so for these, I'm more likely to ask you to list things rather than to ask you to explain these. That's the end of that.